Hi guys and girls, today I'm going to kind of take a break from the functional analysis sub-series which has only just started, but anyway, it seems like because the academic year is approaching, some of you guys would probably prioritize just moving on to integrals, because the real analysis part of calculus is often done at last. So I'm just gonna overview. I'm going to give you an overview of what definite integrals are and the theory behind it. So definite integral theory. Just a quick reminder: a definite integral is just like any other integral, but the only difference is that it measures the area from one point A to a different point B, rather than just like a general thing. So an indefinite integral would be just an antiderivative, the opposite of a derivative. So for a differential or a derivative, an antiderivative operation would turn it back into a function, and then from there, the second antiderivative operation would turn it into an integral, which is called an indefinite integral, or an antiderivative, as I mentioned before. And that just shows you an expression which can be used to find the area under the curve from one point to another. But the definite integral is like what you get when you actually do that. It's like the area from A to B as a number, as the actual area, rather than just an expression which is very generic. So some properties which I have to discuss, some of them are quite self-explanatory, but others aren't so much. So the first property we're going to discuss is the net value. And that says that if we have, just going to move this a bit, if we have a curve here, and it's going to have some parts above the x-axis and some below. I think my channel promo kind of has this kind of picture. So this part would be negative area, and this would be positive area. And if this doesn't really make sense to you, then just visualize that you're trying to find how much of something. So for example, integrals in motion problems, you would have a positive integral here. The area under the curve above x-axis could be how much you have walked, and then you suddenly, if it's velocity, and then suddenly you have this negative curve, it could mean that you're walking backwards. So then in your total integral, how much you walked in total, of course it wouldn't, the total this amount of displacement, the displacement you walked, wouldn't be equal to the area of both of them together, because clearly if you walked backwards, then your displacement is getting reduced. So that's one intuition for why that is the case. However, if we do want to find the total area kind of drawn by the curve, regardless if it touches the positive x-axis or touches or it goes under the positive x-axis, it doesn't matter. If we find the absolute value, then we would have to walk out separate integrals, which kind of preludes this thing here, integration path, but I'm going to show it later. So then again, so if you're trying to work out the integral, say this is f of x, and the integral of f of x here would give you the value of here of this part of the curve minus the area of this part of the curve minus the area of this part of the curve. If you're trying to find this whole thing as an absolute kind of area under the curve, then you would really be doing separate integrals. So the integral from a to b here. So you do integral from a to b of f of x plus the absolute value of this thing over here, of the integral from b to c. So yeah, so now I'm just going to quickly jump to what this last property here says, because I think that's probably the most relevant here. So an integral is just an area. You can add areas up. You can, just like you can add up trapeziums, there's no reason why you shouldn't add different parts of an integral. So imagine if this was curved and this part of a function, and it had different parts. There's no reason why you shouldn't just add them together. So that means that that kind of redirects it to this rule over here. And I kind of worry that I'm confusing you, but when you split an integral, what you're doing is you're turning an integral of f of x plus g of x. You're splitting it into two different integrals, so an integral of f of x and an integral of g of x. So that kind of applies to here. The same way as you do that, you can also split an integral by its bounds to a. So if it's a to b, then you could do a to c and then add that integral to an integral from c to b. Just like in vectors, vector ac is the same thing as ab plus bc if b is a point. So so with integral splitting, there's nothing really. It's just like you have in derivatives. You have a derivative function, and if it's too complicated, you can split into different terms by the subtraction and addition rules. When reverse integration is very interesting, because in this third property of integration, it says that if you have an integral from b to a, that means you're reversing this whole operation. So it's the same thing as doing it from a to b, but then adding a minus kind of symbol in the beginning. Then instantaneous integral is quite easy, based on the intuition that when you find the integral, you're finding an infinitesimally width kind of trapezium. Then of course the area of that integral, if you view it that way, would be 0, because if it has an infinitesimal amount of matter, if it has an infinitesimally small width, then you can't find its area, because it's virtually 0. It only matters if you have a whole kind of spectrum of lines there that advance towards a different bound. Then you can find the area, but you can't find the area of a given line. And that's exactly what an integral from bound A to bound A is, because if it's A to A, then it's just one line. So that's intuition for property number 4. And yeah, I don't think there's much else I can show you. But in the next video, I'm going to show you how to use the reverse power rule, which is basically the most fundamental thing about integration, and why it's the opposite action of differentiation. And hopefully also, rather than just talking about concepts in calculus which I view as fundamental, I actually talk about the fundamental theorem of calculus, which is essentially the most fundamental theorem in calculus. And I'm going to show you what it is and why it's just a formula way of presenting what I already told you about what integrals are in relation to differentials or derivatives, and how to shift from one to another. Just see you in the next video.